everyone. Welcome to the podcast. Ben Tremblay received his PhD in solar physics from the Université de Montréal in Montreal, Canada, under the guidance of Professor Alan Vincent and Paul Charbonneau. In 2019, he joined the Laboratory for Atmospheric and Space Physics in Boulder, Colorado, as a George Ellery Hell postdoctoral fellow to work with Professors Maria Kazasenko and Benjamin Brown. For the past 2 years, Ben has been working at the High Altitude Observatory with Anna Malanusenko and Matthias Rempel. However, this week is his last week at HAO and in Boulder. Tears. His next appointment will be at Environment and Climate Change Canada in his hometown of Montreal. Over the next year, he will be transitioning out of solar physics to focus on weather, climate, and climate change studies, and to find more worthy competition at football than Momo. Okay, to Ben, today he will be speaking on spectral irradiance of the 3D sun.
All right, thanks everyone for joining. This is definitely a bittersweet presentation. After 5 years on Boulder, it's kind of sad to say goodbye to all the people I've met throughout the years. And for today, I'll talk about a project that involves some of the people here in Boulder that we started about 2 years ago, and that will continue after I leave. It will be in the hands of Robert Yerlin and Andres Munoz. And it's a project called SPIS, or Spectral Irradiance of the 3D Sun. And to give a bit of context, this is a project that's part of a program called the Frontier Development Lab, which happens every summer. It's basically a research sprint. You could think of it as like a hackathon, but over 2 months. So it's pretty intense research. We have a few people that have done it here, including Jordy, who's in the room. So yeah, we started this 2 years ago. We continued as well this summer. There's more people involved in the project than the faces you're seeing here. I'll introduce them later. But yeah, the goal of this project is to use artificial intelligence to try to make a 3D model of the sun so we can get new perspectives and maybe do new science, or try to look at things from a new way. As well as in the process try to estimate spectral irradiance. And this idea of making a 3D sun is going to be motivated by a lot of science, which I'll briefly introduce. So to give a bit of an outline, I'll provide an introduction on our project from 2 years ago, which focuses on the idea of making virtual satellites and virtual instruments. And what this means, I'll introduce in a minute. We'll then move on to the SPIS end-to-end deep learning pipeline, which will enable us to do a few things, one of which being making a 3D plus temporal representation of the sun, or if you'd like, 4D. It's just 3D allows us to use our acronym, 4D does not, so 3D plus temporal it is. And then we'll talk about how we can estimate EUV spectral irradiance from EUV images. I'll introduce some results, which may provide us some new perspectives of the sun. And then I'll discuss about ongoing work, which started this summer that will probably continue over the coming years, which was part of this new edition of the Frontier Development Lab, which the project went from SPIS to now SPIS on Mars. So first, let's talk a bit about motivation. Why are we interested in trying to look at the sun in 3D? Well, from the perspective of the sun itself, well, we'd like to understand a bit more about its dynamics, of course. A lot of us are interested in solar flares. Having a 3D perspective of it could be quite interesting. And such events, of course, have an impact on us in a way. The sun will have an impact on our assets in space, for example, causing satellite drag, which, with our community being so technology dependent, this could be pretty impactful. But then again, looking at the relationship between the sun and Earth will allow us also to better understand the impact on other planets in the solar system, as well as outside of the solar system. So looking at the sun-Earth connection could maybe help us understand a bit more the connection between other O stars and the planets that may be orbiting around them. And then finally, the sun is, I mean, an ideal template, of course, to study other stars, because it's the one that we can actually spatially resolve and study. But of course, there's limitations. Most of our observations, for example, are ecliptic. But then for other stars, we don't know what the inclination of the star is, or etc. So if we could have it in 3D and really start spinning around that sun, then that would enable us maybe to see things a bit differently. So in order to get there, let's talk a bit about how we view the sun. And I'm going to be using a lot the timeline of 2010 to 2014 to discuss the project. But of course, we have Solar Orbiter now and other things. But just to introduce some ideas, let's focus on the times where we have like SDO, stereo A, and as well as a functioning stereo B. So for example, with a satellite like SDO, we get basically an Earth perspective of the sun. We're able to capture images in UV, so really like spatially see what's happening with, for example, SDO AIA. But then SDO is also equipped with EVE, and EVE has different irradiance instruments on board, like MEGS A, MEGS B, which allows us to measure spectral irradiance in extreme ultraviolet. And here, irradiance is basically a measurement of the power emitted by the sun at a given point in space. But that's basically, yeah, the Earth perspective. There's other satellites going around the sun, like stereo A and stereo B, which are capable of capturing images of the sun in EUV, not necessarily in the same wavelength as SDO, but in their own set of wavelengths. And what's neat about them is that all of those are on the ecliptic plane, so they're basically orbiting around the sun, viewing it from an equator perspective, if you like. But stereo A is pulling ahead of SDO, and stereo B is pulling behind of Earth. So we're getting from these positions, we're basically getting different perspectives of the sun. So in a sense, you're kind of seeing the sun in, if you like 3D, you could put it on a flat sphere and look at it. But yeah, we'd like to be able to do more than that. For example, like probe the atmosphere. And also, stereo A and stereo B, while they get us images in UV, they don't measure irradiance, which would be potentially nice to estimate prior to the sun being intervened. So these are kind of like examples of how we view the sun using satellites. If we'd like to get new perspectives of the sun, there'd be a solution, which would be, for example, just place more satellites in space. But we argue that we can actually just leverage what we have right now, which is already great. And that's already like a huge wealth of knowledge. We can try to leverage what we have and make something that we'd refer to as a virtual satellite. So learn from, for example, from stereo A, stereo B, and SDO to have a satellite that's technically not real, but that you could position them at any point in space to study the sun from a different perspective. And that, for example, in this, we put them on the ecliptic plane between the different satellites. But because it's virtual, you're no longer necessarily tied to such an orbit. You could have fun and try to go like non-ecliptic and really try to view the sun from a different perspective. Of course, we have Solar Orbiter now, which enables us to do this. But let's assume again the scenario like where, let's say we don't have Solar Orbiter. So we could technically break out of this and really view the sun from a new perspective. So we have this concept of virtual satellites that we'll look into. And we propose to do this using AI. But with AI, we can do another thing, which is the concept of virtual instruments, where, for example, we could add new capabilities to existing satellites as well. Like stereo A and B can take UV images, but they can't measure radiance. But we can try to use AI to make it possible for them to infer radiance, not measure, of course, but infer irradiance based on the other measurements that they produce. And so this is a concept that I'll refer to as virtual instruments. This is also used even for SDO, because SDO is equipped with MEGS A and MEGS B for irradiance measurements, but MEGS A malfunctioned in 2014. And since then, part of the EV spectrum for irradiance is not measured. Having a virtual instrument could potentially replace the malfunctioning MEGS A. So these are the kinds of ideas I will try to explore. So if we had to summarize it in two basically branches for the presentation, I'll first talk about virtual satellites, and this is going to be related to AI model that we call Sunners, which will enable us to make a 3D model of the sun and get new views of the star. And then we'll focus also on virtual instruments, which in this case is going to be called MixAI, to try to make spectral irradiance inferences starting from EUV images. And then the two of them combined will form our SPI's pipeline, which I'll introduce later. First, very briefly, I want to talk about neural networks because this is going to be neural network heavy. But I also want to keep it simple. So if we have a neural network, we could basically break it down as something like this, as a simple function. So if you have observables or inputs X, a neural network is just a function G that you apply to this to get an output Y. And really the interpretation of that function is that it's a fully differentiable function approximating the mapping between X and Y. For example, I've mentioned the irradiance. We would basically have X be EUV images and Y be the irradiance. And then this function G is just a relationship between the two that we're trying to figure out. What does the function look like? I mean, in its most simplest form, it looks something like this. So you have a vector of inputs, like x1, x2, x3. You have a neuron, and then you get an output out of it. Basically, if you again want to just write it down as a mathematical function, it will look something like this. For each of the inputs, x, you're going to be applying a weight, W, and then afterwards adding a bias. And those weights and bias are adjustable. These are things that you're going to try to optimize for whatever task you're trying to do. You're then applying also an activation function over this operation. And this is done so that you can do something that's nonlinear. We could assume, for example, that f is just x. So this would be just a linear operation. Super simple. That's your function. But you know, a linear function is not always a good approximation of whatever you're looking at. So if you want to make something more nonlinear, you can come up with a function f as long as it's differentiable. So again, if we look at this neuron, really the interpretation is just a fully differentiable function with adjustable parameters, W and B. And these are going to be dependent on the task. Actually, one of the neural networks that we'll be working on today is basically just that. So pretty simple, just a linear function. But of course, you can have multiple neurons together if you'd like to make your function more and more complex. So even if like going through the first neuron still looks simple, now if you put this in the next one, then you can see how your functions become increasingly more difficult to interpret, but might still be useful for the task you want to do. And then you can go all out with it and really make it more and more and more complex, but also more and more ugly and difficult to interpret. And that's one of our neural networks is going to be something like this. Specifically, the SONARs for the 3D reconstructions is a model kind of like this. There's not much more that we need to talk about in terms of the neural networks. I think this will be hopefully enough to grasp the ideas. And before we get into the projects themselves, I just want to talk a bit about data. First of all, we're using EUV images, and I'll focus mainly on EUV images captured by SDO AIA, as well as stereo UVI for stereo A and B. But as you know, for example, SDO AIA can observe in multiple wavelengths, and stereo A and B will observe only in 4. So it's not the same subset of wavelengths necessarily. Some of them are close, but some of them are not shared at all. And to simplify a bit our problem right now, because these are 3 different instruments, and they might not necessarily be consistent with one another, which of course complicates things when trying to do some interpretation. We're going to cheat a little bit, and we're going to use AI again to basically translate images from stereo into AIA images. And prior to this, we're going to be, for example, downsampling spatially the images so that they're similar in resolution. But then you can train your neural network to try to map stereo to SDO. I'm not saying it's necessarily like the right practice to do. In this case, it's being done just to simplify as much as possible so that we can treat the problem as if we had 3 of the same satellite. But I'll mention later an alternative to this that we're currently exploring. So for this, we're using Robert Yellen's instrument-to-instrument translation tool, ITI. And then when it comes to irradiance, we're going to be focusing mainly on the irradiance captured by MixA on board SDO Eve. And that's the instrument that malfunctioned. So we have data from 2010 to 2014, and our goal is going to be, first of all, to try to replace it, and then to try to put it on other satellites, not just STO. Quickly, just instrument-to-instrument translation. It's a generative adversarial neural network that we use to try to map data from one instrument to a different instrument. I don't want to spend too much time on it. I know Robert's been working on a paper. I think it's still being reviewed right now. But the idea here is that the tool's been developed to try to translate stereo into AIA. And so we're going to be using this just to basically make our stereo data AIA-like for simplicity for our problem. Again, not necessarily the best practice in this context, but it's just easier. Okay, so let's talk about our virtual satellite. And for this, the method, we call it sun neural radiance fields, or SUNNERS for short. This is a sketch that kind of summarizes the idea, but we'll go more in depth about it. The idea is, first of all, to start with multi-viewpoint satellite data, like I mentioned, for example, with SDO and then stereo, giving different angles. We're going to be using their images to try to make a 3D model, which is also time dependent, so really it's 4D. So we'll have basically a sun in a box, in a sense, that we'll try to generate from these images. And then once we have a sun in a box, we can then position an observer at any position around it as we'd like. And from this, we can look at the sun from new perspectives, not just the one seen by satellites. And that includes, again, like breaking out of the ecliptic, maybe seeing the sun like closer and closer to the poles or something like this. So how does this work? So first, let's talk about neural radiance fields. Oh no, the video. Oh, there we go. Okay. I will have to pause from time to time. I might have to stop. Okay. So I will maybe do it like this. So you're seeing a bunch of weird squares in this video. Those are meant to be like frames for images. Assume these are all different observers, or to translate to the sun, let's assume these are all different satellites. Each of those are capturing images of the object in question. Here's going to be a Lego toy, but just assume it's a sun. I mean, it's yellow, so of course it's the same thing. But basically, you have this image captured from a given position. The way neural radiance fields work is that you're going to trace a ray, basically a light ray, from your observer, which would be like this small little window here, through each of the pixels of the image. And then this ray is going to travel into the volume that in which you're trying to reconstruct your object. Along that ray, you will be sampling points. Basically, these are points within the volume. You're defining an X, Y, Z, and also a T for time. At each of those points, the goal is then to write a neural network that will translate position, and of course, and in this case, they're also putting, for example, the position of the observer, but we can ignore this. You want to translate X, Y, Z to some properties. In this case, these methods were developed to estimate RGB colors, as well as the density of the object, which does not apply for the sun, but I'll get to that in a minute. But just to illustrate the concepts, you're going to try to train a neural network to do this. Translate basically position to an estimate of what the color should be at a given position along the light ray, and then how dense this should be. Once your neural network is trained, you'll see how the points change colors. Basically, it could be assigned a value. But once you estimate your values along the light ray, you're going to integrate it all the way back into a pixel. And this is something that people are very familiar with. It's radiative transfer, but here with RGB colors. So, but that's basically the idea, is that once you have a volume and a light ray, you can then integrate it and recover a pixel in your image. And then you can compare it with the original and optimize your neural network based on this. But we have this for multiple positions. So we can trace a bunch of rays to do this process, and then the next thing you know, you end with a 3D model of the object that was within the volume. This is a technology that's been quite popular in the industry at the moment. Like, for example, You can use this for a lot in video games to render things. And basically, for example, instead of having to store a 3D object, now you're just storing weights and biases in a neural network. You go from something that would be gigabytes to something that's just a few megabytes. And all you have to do is optimize this function that takes position in the volume and then estimates this color and density. But now, the Lego toy is not a sun. And basically, this only will reflect light. The sun is an optically thin plasma. There's absorption, emission, all those things. So we have to modify these kinds of approaches to work and be actually physically relevant to the problem that we're looking at. And this is where we introduce a method like Saunders, where you'll see that the steps are all very similar. It's just what we try to compute is going to be a bit different. So I'll walk you through the plot again, and you can think of the video from before for inspiration, but you start with your satellite and images that it captures. You trace a ray from the observer to the pixel in the image, and then inside, all the way inside a volume. This is the volume in which we'll try to simulate our sun. Inside the volume, basically along the array, you're going to define points, which are in red. These are our sample points. These are where we'll try to produce estimates of whatever quantity we're interested in, and that's going to be basically the product of our neural network. Those points, they're going to be, each time we train a neural network or each iteration of training a neural network, these points are randomly selected. So it's not like we've defined a grid or anything, which is also another interesting aspect, which I'll get to in a second. But basically, you do this to all the pixels, and then you also do this technically from different angles. But for a set of sample points, what you do is you will provide the position of a given sample point, X, Y, Z, and also time, as input in the neural network. And that's where the neural network comes in. It takes the position, goes through it, and then as outputs, it produces something. But we're not interested in RGB, of course. We're interested in science. And our science here is going to be emission and absorption at each of the points in the volume. So these are like coefficients. And once you've defined them, all of them along the light ray, you would basically get kind of a curve like you're seeing here. But now you're going to use radiative transfer to integrate along the light ray and recover back your pixel, and then compare it with the pixel that you started from. And then you repeat the process in a loop, and in the process, you adjust the weights and biases of the network. This kind of neural network is doing something that typically in machine learning, you will get told not to do. This is overfitting. It's a concept of basically training a neural network to do just specifically one thing only. It doesn't generalize. So if I train, for example, a neural network using images from AIA and EUVI from the month of January in 2011, that's all it can do. It won't, you can't use it to go beyond. It is meant to be making a 3D model of the sun that's valid specifically only for when there's data published. And so for this reason, this works a bit differently than your classic neural networks. Another thing to note is that this version of the neural network is, of course, wavelength dependent. We're going to be assuming here a single wavelength for all the images that we use. So for example, 193 angstrom. We're only using 193 angstrom data to make our 3D model of the sun. How to use all the different wavelengths we'll discuss towards the end of the presentation, but at the moment, again, for simplicity, we're focusing on just one wavelength to make this kind of 3D model. So that's two key factors to note. One, wavelength dependence. Two, only valid for whatever set of data you trained it on. So treat it kind of like it's making a 3D model of existing observations. It's kind of interpolating in a sense, except now it's 3D, so you actually get a new dimension that you can potentially use for some science or something.
So should I only really care about the output from this in terms of the 3D model, or do those, when you have those like red dots, the sample points, are those emission and absorption coefficients meaningful? Like, is this saying that that's what the sun is doing? It's emitting at this point and it's absorbent at that point?
Yeah. So maybe to clarify, for example, once you finish training, you now have this function depending on x, y, z, and t. And whatever value you provide to all those four parameters is going to spit out a absorption and emission at that given position and time. I understand that, for example, those quantities might not be of interest in a 3D fashion, but we'll get to an example that might be more
I don't
beneficial.
mean so much whether they're of interest, but are they real? Or like, are you saying that the sun is absorbing in UV to that extent?
Well, the challenge is we don't know because we don't have a 3D data set, but we'll get to that in a second. There's going to be a lot of stuff like that where we have to kind of question what we're doing in this presentation, but we're trying to do things to try to validate these ideas. But in principle, yeah, you can make images kind of like with the satellites, and it looks good. Of course, is it valid? Don't know. There's no satellite there. But when it comes to the 3D, it's even more complex because we just don't have access to this information. So we can make an estimate, and there might be ways of us trying to assess if it makes sense or not. But in most cases, we just don't know. But I'll get to that in a second. So this.
No, but it's physics informed still.
Yes.
Because it has to abide by a radiative transfer equation. So there's some constraint.
There's a constraint.
That is physically based, right?
Yeah, there's a constraint, but at the moment it's still a bit, let's say, simplistic.
Yeah.
I'll talk about how we're trying to make this more and more physically accurate, which is where the work is currently at. But maybe to Paul's point, how do we check? Well, with the real data, we can't necessarily do that, or there's limitations in doing it. So what we had done was we had worked with the people from predictive science who make these global simulations of the sun. And they basically made renderings of what the sun would look like as seen in a certain set of wavelengths. And this, in a sense, gives us different perspectives as if we had different satellites around their simulation. And the idea is also that technically with those simulations, we could have access to cubes and then study it. But then with these absorption and emission coefficients, it's still a bit. We couldn't necessarily do that comparison at the time. Again, I'll come to that at a later point. Here, I'll present an example of trying to validate the approach using just the rendering. So just the 2D images, not necessarily the cubes, but what you're seeing on the right is a video of what that simulation looks like in different wavelengths. And it's important to note that it's static. This one is not time dependent. This is from not this year's eclipse, but from a previous eclipse. They have made a model. It is static. And as a result, we can't necessarily test out this time aspect. But we have on the left an example of the different positions at which the group from PSI rendered images in UV. So you see it's all over the sphere. The points in magenta are basically like ecliptic perspectives. So they're within plus or minus 7 degrees. Everything in green is non-ecliptic. Because we wanted to replicate a scenario that's kind of like SDO and stereo, what we did was only showed the ecliptic data to the neural network. So we have 32 vantage points. So 32 images.
How do you get the information on the solar poles?
Well, there you go. We're going to get to that in a second.
Okay.
So in this simulation, they come up with something. How they do it, I don't know. We'll have to ask them. But here, our objective is seeing if we train a neural network using just ecliptic data, is it enough to recover non-ecliptic views? You see the poles just a bit, but is it sufficient? And having it from multiple angles. The answer seems to be yeah, question mark.
So you use all of those ecliptic
Yes.
points.
Which again, not necessarily realistic from the perspective of real observations.
Just curious.
Yeah, but it's 32 static points around their simulated sun, all ecliptic. Only use that for training, and then we see if we can go non-ecliptic.
And can I ask, do you use the views on the disk as well as the limb?
Yes, both this can. So we're also trying to recover the limb. So if we look at the first row, this is the ground truth. So that's renderings from the simulation. As you go from left to right, we're looking at different latitudes. So we're staying at the same longitude, but we're changing the latitude. So the first two would be like ecliptic. So these would be part of the training set. So those first two columns, treat them as like training data. So ignore the results from the neural below because that's from the training dose, so that's kind of not fair. But you get from ecliptic to non-ecliptic and then eventually up to the poles. And below is what the neural network produces, learning only from the ecliptic perspectives. So of course, ecliptic is saw during training, so it's cheating. Let's not look at this. But look at, for example, the latitudes as we increase. And in general, the rendered images look quite similar to the simulation. They're not like 100% match or anything like that. There's differences, of course. But in general, still, it looks like we're able to produce a view of the poles that's not too far off from what's in the simulation. Of course, this is very idealized and everything, but it's still promising that even just ecliptic images allow us to make a model that seems pretty decent. So that's one aspect.
This is for 32, you said.
32 viewpoints.
Have you like decreased that and see how many theories before you don't recover it anymore?
Yeah, so we tried experimenting with this a bit. There's more work that needs to be done, but we decided to switch to a different type of validation, which I'll mention later, because we had issues here with the finite static. It's not necessarily the best way of validating the problem, but now with their new simulation from earlier this year, we can do it. They have a time-dependent model, and we're working with that, which now we will really be able to test out those scenarios more accurately.
So the time evolution helps with the spatial
Yeah.
interpolation, let's say, let's call it.
Yeah, so I was just going to get to that. Once we move to observations, time and the sun's rotation acts as having different viewpoints. So you might only have 3 satellites, but because of how things evolve, it's like having other viewpoints. So yeah, we'll take advantage of that. So that's why this was like a first test that was pretty encouraging. Translating it into observations is a bit difficult, which is why we're switching to their new simulation. But time is the key factor in making this possible for observation.
Have you tried doing this and blocking out the disk? Because the information you get at the poles is essentially limb only. Because
Yes.
And so if you blocked out the disk, your poles would be no different from your equator because the limb observations are identical regardless of what latitude. But the disk have a huge difference if you're at the equator versus poles. So
Right.
if you blocked out the disk and did this, I bet you would also get something that looks kind of right, even when you reconstruct the disk from only limb observations.
That's an interesting idea. We did not look into this.
Yeah.
So no, I mean it'd be worth tell Robert he's picking up this project. So
But you could also do it from coronagraph observations. You could reconstruct information on the disk from the limb observations by doing this kind of thing. Because that's what you're doing at the poles.
Right.
You're using limb information to get information about the disk at the poles.
Right.
yeah, there might be potential there. That's true. But yeah, we didn't get to try that. No.
Question.
The mapping function is
Doesn't
inherent
it
from the-
really depend on the assumption that the emission is optically thin?
Yes. So this we're all assuming optically thin purely.
Okay.
And also, for example, when I mentioned those light rays that we trace, if we get to the solar surface or just slightly above it, we stop the ray there. Like we don't try to go close to the surface, so we don't try to go inside. We accidentally did that once and ended up with a transparent sun. It was very yeah, and this is just another quick kind of way of looking at the similarity. So not errors or anything like that, just similarity between the images that we produce. Peak signal to noise ratio and then self-similarity index. For example, PSNR is a quantity that the higher it goes, the more accurate you are. And SSIM, the closer to 1 you are, the more accurate you are. The 2 lines in red represent the ecliptic. If you go outside of those red lines, then you're non-ecliptic. And as you can see, even if we go out of the ecliptic, still the values don't change too much, which means that there's still a pretty good match in terms of what's in the simulation and what we reconstruct. But
so signal to noise. Noise is the difference between the simulated and the truth, or the predicted
yeah,
and the truth.
something like that.
Something like that.
So again, simple validation we're trying to work on something that's a lot more detailed than this, but the cool thing is the observations. Yeah.
Coming back to the assumption of optically thin, when you go to the limb, it's not necessarily optically thin.
Mm-hmm. Yeah.
A long path length in the atmosphere.
I would think you said it was optically thin, right? Because you had absorption coefficient as a function of your path as well, right? So you're not assuming it's optically thin. You've got emission and absorption all along.
Yeah.
And then you just integrate.
Yeah, you're right. It's just in general, we're really trying to treat this as optically thin, but with the equation that we have, technically,
it could be anything.
Yeah, it could be anything. But again, this whole thing of absorption and emission, for example, in 3D, we're still, needs validation. So
Is there a directionality on it for the absorption? So like your ray, it's not 3D, like emission is going to be scalar, right? Basically, but absorption is not necessarily. It cares about what's behind it. And
right. I mean, that's where we're hoping that through the optimization, we're accounting for that integration, starting from the end of the ray at the sun and then integrating back to the observer. So I'm hoping this can maybe account for this.
Optimizing from many viewpoints.
Yeah.
Well, 32 in that case at the same time. So
Yeah.
presumably it has to be consistent internally, right?
Yeah.
Yeah.
okay, so
Rays
there's
from
more
different
points
viewpoints
get
cross.
reproduced. and it comes.
There's likely some intersection, and actually, this is how you're going to achieve your best results: is that if the rays intersect,
Yeah.
because then you're sharing information.
So you don't want a quadrature, you actually want
Yeah,
slightly
off.
quadrature that won't intersect ever because you don't go inside the surface.
Yeah.
Right.
So now we can explore this idea with the observations. We're going to consider a scenario here with SDO, stereo A and B, and we'll focus on 193 angstrom images. Of course, stereo A is 195, but we're going to use the instrument-to-instrument translation to make it more consistent across the board. So kind of like having 3 AIAs for simplicity. So we're using a sequence here of about, I think, 2 weeks worth of data. Between 2 or 3 weeks, I forget, but we're using images during 2012, I think, end of August, at least 2 weeks, in such that with the position of the different satellites and this amount of time with the solar rotation, we're basically getting a full view along the ecliptic. So this is, again, ideal, but we're just trying to test this out. And next should be a video showing what the 3D model looks like. And so we're going around the ecliptic, and now we're going to go non-ecliptic. And also, there was an eruption in the data, and it's in the model. So if it's in the data, then hopefully it can capture it, and it looks like in this case it can. So this is showing you an example that despite learning, from these ecliptic perspectives, once you're done training, you can provide any X, Y, Z, and T to your neural network, and as a result, you can position an observer at any position around your 3D model. Because you can basically sample at each of the points that you need for making your images or rendering your images. And so you start ecliptic, and then you can go non-ecliptic. You can even go over the poles. You can try to basically get a perspective of what that might look like. So, again, it's only valid for that time sequence. Don't try to go beyond it, but this is an example of what it could look like. And if we look at one such example, of course, I just mentioned it, the poles. They've never been imaged. With a model like this, we can, have a first look, and really big quotation marks. I'm not saying these are observations. I'm not saying these are measurements. This is a model. Don't attack me. So despite learning only from those ecliptic perspectives, we can try to see if we can produce an image of it. Katie?
Wait, no, don't worry. I'm not gonna attack you. No, but can you delve into a little bit? Maybe you're gonna do it later. How do you kind of separate or account for the evolution that is actually happening during those 2 weeks versus trying to use those 2 weeks of data as as different perspectives and different measurements. Because I see when you do the movie, there are places where you've got like a little brightening that then goes away,
Yep.
and you've got that little kind of eruption type of thing. But at any individual time, you're seeing a snapshot from specific perspectives at a specific time with a specific evolutionary state.
Yeah,
How does that all fold through?
good question. I mean, yeah, it's in this case, like we're literally just presenting it these images captured from a specific viewpoint, captured from a specific time. We tell the neural network that information, like position and time, and somehow it just, you know, manages to sort of interpolate in between those points or like time or position. There might be different ways of us trying to, you know, provide that information, but for now, it was fed as is. Here's images, position, time, and then try to make a connection. Of course, we can end up in scenarios where, depending on the angles between the observers, we might not get, for example, full coverage of the sun. So whatever model we're going to generate is just going to be for a patch or something like that, and then you might have a non-existent sun behind. But yeah, there might be different ways of trying to provide that information, but for now, it was just.
So it's a secret in the network that's not something that was specifically accounted for as part of the physics informed. I mean, like the physics that's being put in terms of expectation of longevity of structures or something like that.
No, it has no information about this. It sees it in, I guess, in the data, but we didn't tell it anything about the different type of structures, the different type of features to expect or anything like that. There's things that we've been looking into, for example, in terms of learning like a background state or something like that. Having the network being trained first on that, and then the network afterwards being optimized basically as residuals, so that maybe this way it could focus more on features. But I don't have an example to show for that. But besides like basically the radiative transfer, the EUV images, and the positions and time, we didn't tell it anything.
You don't tell it this annotates, and you don't. So you've got three perspectives at every point in time. When it generates a new 3D image at a new time, it forgets everything it learned from the first time round, or does it somehow remember what it generated from a previous time step?
Well, through this optimization process, the things that we're really using to match are the existing observations. So it's always going to be seeing those. The thing that changes.
It gets everything all at once.
Yeah, it tries to get all of those at once. The thing that changes though is the points along the ray that are being sampled. This is always random. So it's going to be like, you can think of it as being the same rays. The points though are always going to be changing. So in a sense, in the volume, whatever you're sampling is different. But you still want the integration to end up with.
Sure, but I guess what I'm trying to say is at every time step, is every time step independent?
No.
Different time step?
Think of it as it's three-legged position. Time is like just another coordinate. It doesn't know like, oh, this is time step one, and I need to move it forward in time. No, it treats it as position. So from that perspective, yeah, that's kind of how it works.
So the randomizing the rays is just a way to bog it down with like too many coordinates to record that point.
Yeah.
So it's just more efficient and
It's
achieves a smooth solution, but you don't have to test all of the points every single time.
exactly, and at the same time, this is a way of, because you want this function to be valid at any point in the volume. If you are focusing on the same points,
Yes.
there's no guarantee you get anything valid in between.
Yeah.
So you're basically coming up with a spectral plots of the sun in various wavelength bands, but not a spectral energy distribution.
Not in this case, no. But there's potential. We'll get to that.
Can I just ask a quick question? If you
Yes.
the output of your fitting, the output of your learning is those absorption emission coefficients for X, Y, Z, and T.
Yes.
Okay. So the time is in there, but by learning this 2 weeks, at two locations, you basically produced a 3D time 4D cube of epsilon and absorption.
Exactly.
Okay.
Yeah, so this is an example of the solar south pole in the model. The arrows around the image in the middle are showing you the positions of the different satellites. So like red was stereo B, SDO was in blue, and then stereo A in green, just so you see kind of the overlap and how we get a full view of the sun if you assume that it's not moving. And one of the things that we were trying to see is like if we have a perspective like this, and for example, we try to segment the boundaries of a coronal hole based on the images that we have on the left. You know, you see a bit the polar coronal hole, you could try to trace the boundaries. If you project it, you would get basically the blue outline in the middle. And then if you try to use our approach of like using ray tracing and everything, we see that, for example, we're seeing boundaries that look a bit different. And we're, you know, I'm not drawing any conclusion from this. I'm just saying, hey, you know, we're seeing things a bit differently than if you just took the images as is. And this is it at 193 angstrom, but we train models for each like other wavelength, like 171, 211, 304. You might see some artifacts with S2 because of the sun being in this like spherical box. Sometimes it might do some weird stuff, but in general, as you've seen, we can do.
So the 304 line might be absolutely thick.
Mhm.
I've never seen any calculations that show whether it's absolutely thick or thin, but it could be.
Yeah, but in this case, with this emission and absorption coefficient type approach, we still get something. Don't know if it's valid or not. We don't have images of the poles yet, so can't prove us wrong yet.
Have you tried looking at, because I'm looking at another thing, so when you do the boundary, because you can do that, you can trace the boundary, you can also trace the coronal boundary, try it low down using 1080, for example. You can get a difference when you have the coronal emission projected on top of it, and especially at the limb where and the poles you've got you're pretty much just looking at limb. You're going to get all this bright stuff in the corona kind of in the way. So I'm wondering if it's doing a better job or a worse job for that, and that's something you could check on the PSI.
Right.
So
Yes.
if you took the PSI and you traced the boundary, and then you took this one and said which one's the true boundary from the ground truth.
Yes, that would be an interesting test.
Yeah.
I think Robert has started looking into that, but we just never went back to it. But yeah, I think that's a good idea. But speaking of coronal hole boundaries, well, we have something in 3D. So now we can actually study things from a different perspective. No pun intended. But let's look, for example, at stereo observations. This is what we have on the left. And I'm removing the limb here just for simplicity so we can see just the disk. If I fix a longitude and just trace a line in red when we go along it, we'll see different features like a coronal hole, a filament, you know, a few different things. We train the neural network during that time sequence. So now what we can do is basically re-render that observations, but from a different angle. This is what you're seeing in the middle. It's basically this, but now the red line is on the limb. So basically taking it and rotating it. And what I'm plotting over here is basically like the height, or basically up to a certain radius above the surface. And in the back, you should be seeing like radial emission. And what's interesting is that as you go along it, sometimes you can sort of pick up where some of the features might be. For example, sorry, if we integrate it might be easier. Let's go on the right. From this, it's hard to see, but if we go on the right, for example, total radial emission, as you can see, for example, above the active region, peaks. If you go to the coronal hole, you get a dip. And then with the film, there's a dip, which sometimes other places are not too far off that, so it's not the easiest to pick up. But for example, the coronal hole, it's quite obvious. And so this could be a different way of kind of segmenting these features using the 3D information, which would be interesting. Again, we didn't really do anything with this. We're just saying, now that you have this in 3D, maybe we can look at things a bit differently rather than just focusing on the 2D image.
Yeah, what you show in panel D there is not what I would see if I looked at the limb of the sun, like, because
Yes.
that would be looking along the line I say, but you're plotting what I would see looking.
Yes.
into it.
Yeah.
I mean, yeah.
Okay, I interpret it as a plane of sky emission.
No,
as
no, this
opposed
is
to
like cutting a
looking
slice.
down
Yeah.
through it.
Yeah, it's kind of looking like
Kind of a
this.
slice, you said, but the emission from a 2D plane, or the emission. I understand that it's not integrated along the line of sight.
Yeah.
It's the emission from that plane, not looking down.
Yeah, from that plane,
Yeah.
But yeah, it's what we're trying to illustrate here is just this, having this in 3D might provide some new perspectives of what we could do with this or how we can study what we have.
I would really be interested in seeing the 3D shape of the coronal holes that you're getting,
Right.
you know, in general, but not just polar ones, but the ones on the disk. And can you visualize that, like show them as a kind of a, you know, a valley
In principle, we could.
topographically or somehow, or that could be really interesting.
Yeah, and I think in principle we could try to do something like that, but haven't gotten to it yet.
And there's all sorts of interesting connections to radio observations, I suspect, as well, because of the way radio has sensitivities to density and with height.
And riffing, if I can, riffing on what Sarah's saying, you know, things like the extrapolations in terms of coronal holes, you
Yes.
know, from the magnetic boundary. So okay, we can riff all.
Yeah, no, those are all great ideas. And speaking of looking at things in 3D, for example, I mean eruptions. This is an example of the neural network trained only on a patch. So we took two viewpoints in this case, which was stereo A and SDO. And then based on what they were observing, it was just a fraction of the sun, but we can still try to make a 3D model of that. And in this case, it was to try to look at an eruption that was happening. And so you're seeing kind of like this is the model on the left. This is not observations. This is from the model. And then you get height information and information about where the different structures are at. Like you can use absorption as a proxy for density or something like that. And then it might be a different way of looking at this event. I should have made this. The paper's actually been on.
You could do like take time profiles in another dimension.
Principle.
Yeah.
And in this case, we had tried something, it's not a perfect test at all, but we had tried, for example, training the neural network on stereo A and SDO and trying to recover the solar orbiter perspective and then comparing with solar orbiter. And so you have the perspective of the neural network at the bottom and then the solar orbiter perspective here. And the features are kind of at the right place. The contrast is off, but that's because of the instrument-to-instrument translation thing, which was applied for the top images, but was not applied for solar orbiter. So the color is off. But in terms of capturing the features, it's not too bad. But of course, they were really close to each other, so easy. It was kind of easy with solar orbiter being in the middle between the two. So this is just to illustrate an idea, but again, it's very idealized. Okay, and this is the one where we had fun. So because, like I mentioned earlier, we can treat this as a virtual satellite, which means you can fly across the solar system and then look at the sun from all of those different perspectives. For example, here we're traveling sometimes from planet to planet, or yeah, going out of the ecliptic, looking at the different perspectives. And flying near the poles and everything. So this is just, you know, this is just for the visuals, but the kind of thing you can do with a virtual satellite. And this could be interesting in terms, for example, of informing future missions. What can you sort of expect to see if you train on having certain positions, and what should we expect from the different regions, etc. So, you know, there might be some science applications, but it could be also useful for trying to inform what you could potentially see. There's still glitches, like you might see them. I'm saying that we're kind of short on time, so I'm not going to mention much for the irradiance. Yeah, I'll just go to the main idea of it, which is this. So we've also been working on a irradiance tool that translates EUV images into spectral irradiance, which if you look back at our 3D model, we can render EUV images from it. So if you combine it with the irradiance model, that means you can get basically 4 pi irradiance, or radiance from any perspective, which could be interesting from the perspective of estimating irradiance at other planets, or basically getting an estimate of what maybe other stars are producing. Now we can look at different inclinations and everything. So this is what we call our spectral rings of a 3D sun pipeline. So it's the combination of the sun Earth 3D model and then the MEGS-AI irradiance tool. And so there's an example of basically you have a 4 pi view on the left of how the irradiance changes. I think this is based on really old irradiance estimates. I need to update this, but just to illustrate the idea. But now you can estimate irradiance at Venus or other objects. And basically this summer, the goal was to do this for Mars. So now we have spies on Mars. Was this summer's FDL project. I know Ritu's on the call. She was a team member this summer. You have the whole list of people here. But yeah, the idea was to basically take this and try to use the 3D model to get the Martian perspective of the sun. Use the irradiance model so you can then compare with the irradiance measured by MAVEN at Mars. So this would be kind of a way of validating based on measurements. Unfortunately, we didn't make it all the way through. It's still quite a hefty pipeline. So we didn't get to do those comparisons with MAVEN, but I think we're getting closer. But the aspect that I want to talk about, since we focused a lot on the 3D model, is that the 3D model also underwent some changes. And those changes are not complete yet. We're still trying to work on it, but we used to be wavelength dependent. Single wavelength has to be the same across all instruments and everything, which is quite problematic. It's quite annoying because you have to then make sure everything's the same. But different wavelengths provide information from different regions, and it would be so useful to get this. Use all the information available from all different sources. They don't have to be the same across the instruments. So we changed it. We changed the neural network to be multi-thermal. Now you can use all the AIA wavelengths. You can use all the EUVI wavelengths all at once in your optimization. So rather than just looking at 193 and just focus on 193, now you can look at all of them. But this is made possible because we also changed our outputs. We're no longer looking at emission and absorption coefficients. We're looking at electron density and plasma temperature. And then from that, trying to estimate emission and absorption. And that's how we get to use our multi-thermal information. But then the rest is basically the same idea. The only thing I'll mention is now the irradiance tool used to be just like the MEGS-8 channels, which were 14 channels. Now we can do a full continuous spectrum of irradiance. Not just lines, like you can get the whole thing. But yeah, if I show the pipeline, it basically has just changed a little bit. Outputs are different, and now we're trying to do stuff accounting for all available wavelengths. And that's how we're getting more and more physically, I think, interesting. And we're working with the folks at PSI with their new eclipse simulation. And this time, it's not just renderings that we have, they gave us the full cubes. And so we have their plasma temperature, electron density, and from those cubes, we can then render different views, kind of like you're seeing here. So we can make our own EUV images. And from that, then we can try to train the neural network and validate, but not validate based on the images, validate based on the cubes. And this is like, exactly. So now we get to do a in-depth validation, which is what we really need to do. Like the previous one, static 2D images only, so very ideal. Now we can actually look at the cubes and go in details and see if what we're making in 3D makes any sense or not. So we're collaborating with them on this. We were hoping to be able to show some results, but not yet. We need a bit more time to fine-tune things. But the things that we're experimenting with, for example, is because we have this 3D sun, we can also now use existing satellite positions like SDO, stereo, information from a given time period to position our observers there, make our renderings replicating existing observational scenarios, and then see if it makes any sense or not to do this. And then maybe try to take a satellite up and see if we can still make a 3D model right now. So we're experimenting with all those things, but we'll need a bit more time to complete this. So yeah, on with this. So this is kind of a summary of our virtual satellites and virtual instruments. Sorry we didn't get to go over the Irradiance, but happy to talk about it any other time. So yeah, the idea is to enhance the observational capabilities of the data and the data sources that we already have without needing to launch necessarily more. And this allows us to see things from a new perspective, not just science-wise, but like quite literally try to look at new things like maybe potentially the poles. And this, we argue, could be maybe useful to inform future missions. And we're still working on trying to get the density and temperature to be good to go. So that's it. Thank you.
Thank you. Questions? Maybe there are lots of questions.
You home?
So, okay, great. This is exciting. So you're saying you're now learning using the simulation because you have the ground truth of temperature and density, electron density. What is preventing you from, you have all these 3D images and you have the ground truth of the magnetic field. Why can't you just get the BRBCW5 out of it to learn those from the simulation?
The magnetic field is Robert's grand master plan for his future career. So yes, it's in the cards. Basically trying to combine this kind of model with magnetic fields is what he plans to do in the next few years. I think it's very ambitious, but it looks promising.
You think it's possible? It's not like okay.
But at least, yeah, we'll see. He's working on trying to get the funding, and then I guess down the line do this long term. But I should specify, for example, when we say train on simulations or train on observations, really, if I train the network on the simulation, it's to only use it with the simulation, not applying it to observations. This is something to be careful about, not like, oh, we train on the simulation and then apply the train model to observations. We don't. It's only valid for whatever set of images you provided. So only valid for simulation or only valid for observations. They're completely separate. Alan?
How would you go about obtaining an advantage point in magnetic field, since those don't exist?
That's Robert's problem, not mine. I think he wants to somehow combine that. I mean, it would be not just magnetic fields, but also the EV at the same time. I don't know what he's planning on exactly doing, but again, this is grand master plan. I can hear him at night, like, thinking about it, but I won't be involved in that, so I don't know.
You can take the PSI simulations and synthesize Cosmo-type observations. Just saying. Stokes V, Stokes U.
Katie has a question.
Katie?
Oh, just lots of musings. But kind of going back. I mean, I agree. I understand that you can use the what it is for what it is, but it seems like in terms of the going back to using actually observational data and going way back to when you were talking about the emission and absorption profiles or coefficients, basically. And I was thinking about Jeff's question about like, well, such and such may be optically thin, such and such may be optically thick. We don't know. But that seems like that is a way to test, because if you've got the images and then where your errors against the images, if you're validating back against itself, where you have a large discrepancy can tell you whether or not your emission and absorption coefficients are screwy, which could then inform your assumptions regarding optical thickness.
Right.
So you can actually do physics like that already. And I'm also thinking about where you start to bring in the other wavelengths, which are definitely of different. Anyway, it was kind of you can actually use it right now to kind of test some of the hypotheses and actually learn about some of the emission profiles of the plasma. But I was also thinking about this in terms of if you can get your density or your heights, your density integration with heights, you can also do things like DEM measures, and then you've got kind of both more information and a test of information at the same time
Yeah,
or something. Yeah. Okay. That was just
it's something that Robert had suggested doing, and he started looking into it. I think.
okay. We should chat about that at some point. In terms of some work we've asked NASA for money to do. So
Okay.
yeah. Okay. Cheers. Cool.
There was a comment from Vitu early in your talk, and so if Ritu is still there, could you elaborate on that?
Okay, yeah, this is from Shea Weber. We make similar assumptions when stitching together observations of EV observations without ML also. Just pointing out
Yeah.
the same concerns. Oh, I'm hearing Shay, I think.
Yes, we are together in the same room. We were listening in on your presentation.
Gotcha.
Yeah, just people were asking about like the assumptions that are being made in terms of the machine learning aspect, but like trying to stitch together the 304 angstrom data between EUVI and AIA, just, you know, without AI, I mean, you're basically making the same assumptions. It's just whether you actually have to hard code them in or not.
Yeah.
So yeah, there's not a whole lot of difference in terms of what you're I don't want to say taking for granted, but what you're assuming.
Right.
Any other questions, comments?
Half comment, half question. I think the DEM validation is very doable. And it's really important with this new model. If you say you're training all of the filters simultaneously and your functions are in terms of density and temperature, then you need to bring back the SDO field of view, get your map of whatever AI inferred density and temperature is, and then compare it with the distributions from a DM, which is, with all of its cannons and worms, it is somewhat physically constrained.
Right.
And if I would hate it to be too similar, but at least if it's in the same ballpark, this becomes really, I think it becomes feasible. I will start using it routinely in what I'm doing, just changing the viewpoints and getting DMs from it.
Right.
If you show me that this is compatible with the actual full inversion of a DM distribution.
Right. No, I agree. But I think in terms of like next steps, no, this is something we would do in the context of the observations.
Yes.
But right now we're full on just PSI. We you know, because these things look cool, but we really think a really detailed validation is needed. And so we're really just.
But the if you have the same lines in PSI, this is you can do it.
Yes.
You don't really need SDO particularly. That if you have the set of filters, and if it's on a PSI cube, the formalism is the same.
Yes.
To invert that thing.
Yeah.
The thing is with comparing it with against the PSI, it's a little bit of a closed loop that you're, you know, because it's a model that for which things are already prescribed. You know, one of the biggest unknowns in terms of the DEM is like, what is your height integration and the density that you're going to be assuming in terms of getting the full emission measure. So it's, I think with the model, it will be, that's a great thing to start with in terms of validating or testing that kind of, you know, can you infer back some physics, but I think it might be a little bit limited or a little bit sort of too good to be true, you know, with the model.
I see the point, but at the same time, you know, when you train the neural network, it only sees the UV images. It sees nothing about the 3D structure. So I think there's still value in, you know, doing this, inferring the 3D cubes of temperature and
Exactly.
comparing, because it has never seen it.
Right. Okay. Yep. I agree.
I will make the prediction, which is that you'll probably get something different at the poles because this is solar maximum.
Right.
And one of the reasons that the polar view looked pretty good is that there's not a whole lot of change over those
Yeah.
50, 60 degrees of lot of angle at the poles. And this is gonna be a lot more complicated, especially I think it's the south pole that we first. So that'll be very cool to see how well you can reproduce it. And may I just suggest that you say that it's good for virtual satellites and testing things, but you can also put in, you can use it to plan missions of like, what would be the optimal configuration of
Yes.
satellites to truly retrieve to X amount of accuracy,
Yes.
the three-dimensional structure.
That's one of the things that we were hoping to do down the line. For example, with this DSI data, with like, now we can position things anywhere and try to test this out, make our own observational scenarios and see how well this could do. And then we can then, tell people like, hey, if you have this configuration of satellites, this is how well potentially you could do things.
Including out of the ecliptic.
Yes. Yeah.
Cool.
Anything else?
Oh, I was very, I mean, we got a little taste of the Irradiance work yesterday. And I'm very curious about that, but we'll just have to do that another time.
Yeah, yes, you can ping me about
Yep. Sounds good.
I'm under pressure to wrap up that paper, so.
Good.
I was gonna ask, Ben, how much of this are you still gonna be involved in now that you're leaving?
What I was told was that I have about a year to try to transition out. But I'm assuming that as the year goes on, it's gonna be less and less. So, I'll see once I start working there, but they told me a year.
Okay. Any more questions? Okay, then let's thank them again. What is the ultimate part?
Thank you.